So today we'll be looking at a sequences and series technique, and I call it order shifting. And actually, after you learn this technique, you'll be like, why? There might be a better phrase for this, but I learned it when I was really young, and I just made this up on the spot, and I used that name from then on. So it kind of stuck with me. But you can call it whatever you want. But I think I think sequence shifting might be a better word, but that's not the point. I think the important word here is shifting, the word shifting, and you'll find out why in a second. So, basically, for sequences and series, most of you will be familiar with how to find the nth term in an arithmetic sequence, a geometric sequence, and how to find the arithmetic series and geometric series, and so on. And those are really important facts that you should know, and if you're good at using them, then good job. But um, when you get to advanced math, like you won't be using those formulae really explicitly. You have to be more flexible about what you do, and there is a thing about, and there are more things, more aspects to arithmetic sequences and geometric sequences that actually makes it really nice. So, oh sorry. So we're gonna explore that today. We're gonna explore a problem using that. So the problem we're going to look at today is how to find the series, and we're going to call that Sn, of half plus 2 over 2 squared plus 3 over 2 cubed all the way up to n over 2 to the n. So first thought you will have is, oh, geometric sequence, but it's not because yeah, the numerator is an arithmetic sequence and the denominator is a geometric sequence. There's really nothing, so we can't really use a formula straight away. We have to think about it a bit. So now we're gonna just rewrite this. And so first we're gonna just look at the numerator. So it's 1, 2, 3. Actually, I'll write it up to 4 because we're gonna do something with this. All the way up to n. And my dots look kind of weird, so yep. So the numerator is we're gonna focus on the numerator first, and it increases. It's an arithmetic sequence increasing by 1, so it's a pretty simple geometric and arithmetic sequence. So what it means by an arithmetic sequence is that there's a constant difference between terms. So you add the same number to get the next term. In this case, is 1. So what if we copy this sequence? And I'm going to put this in pink this time. What if we copy this sequence and paste it underneath, except that now we've shifted it to the right. So then if we subtract this from this, then we get 1. There's nothing here, so 1, and then this is 1, this was 1, this is 1, and it turns out that all of this is 1. So this n minus 1 is 1, and well, we don't need to care about this for a second. We'll find out about this later. But essentially what we see is we get a whole series of constant numbers, or a whole series of the same number in here. Okay, how do I do this? So we get a whole series of the same number here. And why is this good? Because somehow if we manipulate it like this, so arithmetic sequences, this is a good technique where if you shift the sequence to the right and then minus it from the original sequence, then you get a whole sequence of constant numbers. And if you have a sequence of constant numbers, that makes things a lot easier because in this case we're dealing with numerators. What if the numerators are constant, and if the denominator is still holding its geometric sequence and the numerators are constant, then that will be a geometric sequence overall. So that's pretty smart, you'll think, but how does this help solve the problem? So we're going to try it out now. So now what I'm going to do is multiply Sn by half. So I'm going to multiply Sn by half. And just wait a sec because, yeah, I'll explain why I'm doing this in a second. So half Sn would then be equal to, we multiply half to each of the terms, so 1 over 2 squared, 2 over 2 cubed, plus 3 over 2 to the 4, plus all the way up to n minus 1 over 2 to the n, plus n over 2 to the n plus 1. Why is my handwriting so big today? And then we're gonna copy out Sn at the top, but we're gonna have half. Okay, but so we're gonna write this at the top, but the way we're gonna write this on top of this will be trying to match the common denominators together. So it'll be 1 over 2 has no common pair. 2 over 2 squared. Oh, there's a 2 squared denominator here, so we align it. So it's just a layout. It's no big deal, but like I'm just laying it out like this so that things will be easier to see later on. So if we lay it out like that, it becomes like this. If we try to align the common denominators together. But then we observe something. So that this is why, now you notice why I use these specific colors. Because, okay, wait. If we so what we've done is, okay, I spoiled it, but what we see here is by multiplying half, we've shifted the sequence in some way to the right, like what we wanted to do here. So we've shifted the sequence to the right, because if we multiply half, then it becomes then if we multiply half to some term, then the power of 2 at the denominator increases by 1, and then but the next term has a denominator a power of 2 greater by this by 1. So it shifts. So it makes it so by multiplying half, you make the denominator into the denominator of the next term. So in some way, you're shifting each term to the right. So like we consider it kind of like shifting it to the right, because if we try to align it with the original sequence by matching all the common denominators, we see that it has shifted right. So this is pretty neat, because when we minus this from this, we can not just minus this without having to like match common denominators, because it is a common denominator. We just minus this. So 2 minus 1, 1. 3 minus 2, 2 over 2 squared minus 1 over 2 squared is 1 over 2 squared. 3 over 2 cubed minus 2 over 2 cubed is equal to 1 over 2 cubed. So all the numerators. Yes, I'm gonna just write it out. I'm gonna just, there we go. So we get, so if we minus this from this, we get, this is half, and then here is just minus n over 2 to the n plus 1, and then in the middle here, as I put in green in brackets, the area where everything becomes constant, the numerator becomes constant, and it really works. 1 over 2 squared plus 1 over 2 cubed. So we're just minusing for each term. Plus all the way up to 1 over 2 to the n. So it's so smart, because we know that, so we use this property, we use this clever trick of shifting the arithmetic sequence to the right and then minusing it from the original sequence to come up to see that if we simply multiply half to it, we are essentially moving it to the right, because because it is a geometric sequence in some way. We're just moving to the next term if we try to match the common denominators like this. And also, like, if we minus it, this is just half times Sn. So if we minus this from Sn, then it becomes half Sn. And to find Sn, we just multiply 2 on both sides, and we'll straight away get this. So it's such a smart technique. And what we've got here is a geometric sequence with on the denominator and a constant term on the numerator, meaning that this is a geometric sequence. And now you can use your formula that you know. So we're going to plug that in. But before we do that, for those who are good observers, you'll see that half can also be a part of this sequence. So we're gonna just put it in, but it's a coincidence. Coincidentally, half is a part of this geometric series, and therefore we're gonna put it in to make things a bit easier. So we get this is equal to, if we include this, then since you guys should be familiar with how to do this, I'll just do half times over 1 minus half minus n over 2 to the n plus 1. And then if we simplify this, we will get the halves cancel out. Because this is a half, so these cancel out, and then we get 1 minus 2 to the n. Oh my god. 1 minus 1 over 2 to the n minus n over 2 to the n plus 1. And I'm running out of space, but I can do this. So therefore, Sn, if we multiply 2 on both sides, Sn is equal to 2 minus 1 over 2 to the n minus 1 minus n over 2 to the n. And then, if we simplify this a little bit, we get, and we get this, and then 1 over 2 to the n, so we get 1 over 2 to the n minus 1 minus n over 2 to the n, and that is our answer. And actually, surprisingly, it's actually, so for some of you, it might seem a bit more simpler and more elegant than you expected it, or it might be more complex than you expected it, given that it's actually kind of a really simple style of sequence. But yeah, it's a pretty nice problem. You use some techniques in, so essentially, yeah, we ended up using the formula, of course, but we made our knowledge of sequences and series, of arithmetic sequences and geometric sequences more flexible to investigate some properties of them to actually really creatively solve this problem. So you can try make up some problems like this, like have an arithmetic sequence on the top and geometric sequence on the bottom, or maybe the other way around, and then try to use the same techniques to calculate the value of Sn. So yeah, that was just a nice sequence and series video, and a pretty strange technique that you might not see explicitly in competitions. But the main problem, the main motive, the main takeaway, the main what do you call it, motivation for solving problems is not to see the exact same problem in a test, but it really depends on what you obtain from the problem, like by making your knowledge more flexible or broaden it and stuff. So like here you learned a new creative technique, and you learned that there are different ways to solve these kind of problems. So that's the main takeaway from this. So don't try to memorize it, just remember the creativity behind it. So yeah, I hope you enjoyed this video and hope to see you in my other videos.